A z-score is a standardized value that is found by converting a value to a standardized scale. So for example, we could have a data set of college algebra final exam scores that are normally distributed with a mean of 68 and a standard deviation of 7. Recall that when we have a normally distributed data set, the properties of a normal distribution are that it is bell-shaped and symmetrical, and with a perfect normal distribution, the mean is equal to the median, which is equal to the mode. So with our example, we would have our mean here at the peak, the mean 68, with our standard deviation known to be 7. Well, something else we know about a normal distribution is how the data is spread out. So for example, we expect that 68% of the data would fall within one standard deviation of the mean. So if our mean is here at 68, and we said the standard deviation is 7, then 68 minus 1 would give us this endpoint, or 61, and 68 minus 7, 68 plus 7 would be here, and then this area between 61 and 75 would represent 68% of the data. 68% of the data would be expected to be within one standard deviation of the mean. One standard deviation up to a 75, one standard deviation down. So say we had 100 test scores, we would expect 68 of the test scores to fall in this range. Continuing on with that, we expect 95% of the scores to fall between two standard deviations. So again, if our mean is here at 68, well, 2 times 7, our standard deviation, is 14, and 68 plus 14 would be 82. 68 minus 14 would be 54, and so we would expect that 95% of our test scores would fall between these two endpoints, 95%. So again, if we had 100 test scores, we would expect that 95 of them fall between these two scores. And finally, we can talk about 3 standard deviations away. So here is our mean at 68, and now 3 times 7, 7 being our standard deviation, is 21. 21 plus 68 is 89, and 68 minus 21 is 47. Now this, you can see there's a little bit of data on the top and the bottom that we haven't accounted for, because what we expect now is that 99.8% of the test scores would fall between 47 and 89, 3 standard deviations away from the mean. So that's our expectation for a normal distribution. It's approximate, but it's a guideline that we can use. Okay, so a z-score, as I said, is found by converting a value to a standardized scale. So that standardized scale is called the standard normal distribution. It has this word standard in front of it. It is bell-shaped. It is symmetrical with this sort of a fold line here between the upper portion and the bottom. But additionally, what we know about this is that the mean is equal to 0, and the standard deviation is equal to 1. So this is that standardized scale that we use for creating z-scores. We convert values such as a test score of 90 to a standardized value using the standard normal distribution. Okay, so let's look at what this means with regard to our example. So here's our bell-shaped symmetrical curve, and now let's put what we know. So we had our x values, which were the test scores. We had a mean right here at 68, and we said that if we go out one standard deviation, not very straight, but you get the idea. Okay, we were at what, 75 here because we added 7 and we subtract 7, and we were at 61 here. We went out 2 standard deviations, we added another 7, we got to 82, and over here 2 standard deviations, down by another 7, 54, and finally 3 standard deviations, add another 7, we were at 89, and down here subtract another 7, we were at 47. So this is our data showing the within the 68%, 95%, and the 99.8%. Now, z-scores change these values to a standardized scale where the mean is 0. So I'm going to call this my z-scale, and on the z-scale the mean is 0, and then each value, every time we go up a standard deviation, we go up 1 unit. So 75 would have a value of 1, 82 a value of 2, and 89 a value of 3 on the z-scale. And going the other direction, of course, this would be -1, -2, and -3. So a z-score then tells us how many standard deviations above or below the mean a particular value is. Let's say that again. A z-score tells how many standard deviations above or below the mean a particular value is. So 54 is 2 standard deviations below the mean. Let's look at an example. So Dana made an 82 on the college algebra final exam. What was her z-score? So we could write this as a z for the score of 82, and that's equal to, well, looking at our scale, she made a z-score of 2, because 82 is 2 standard deviations above the mean. Notice that if it's above, we get a positive number. If it's below, we get a negative. So knowing that someone's z-score or some value's z-score is positive means we automatically know it's above the mean. Or if it's negative, we automatically know it's below the mean. Now, how could we actually calculate that too? Well, sure. Let's see how we would calculate it. So Dana's score, we would say, we'll take Dana's z-score would be found by taking Dana's score. We would subtract the mean. That tells us how far apart they are, right? 82 minus 68, right? And then if we divide that by the standard deviation, that will tell us how many standard deviations above or below the mean Dana's test score was. So 82 minus 68 divided by 7. So the difference between the two was 14. Dana was 14 points above the mean. How many standard deviations above the mean? We'll divide by the number of what the standard deviation is, and there we get the 2. So this could be helpful if we know this calculation when we want to find Carl's z-score, because Carl made a 65 on the college algebra final exam, and notice 65 is not one of my x values, so I can't just directly read it off of the graph like I could here with Dana. But I can use this calculation we came up with and say that Carl's z-score, the z-score for a 65, is equal to, and I take Carl's score, 65, minus the mean, which was 68, that's how far apart his score and the mean were, and divide that by 7. And I get negative 3 over 7, and as a decimal, we would convert this to a decimal, negative 0.428, it goes on a bit, but we'll approximate that to 2 decimal places, 0.43. Usually, z-scores are rounded to 2 decimal places. However, you always follow the instructions on the particular problem you're working as to what the rounding is. So now we can see that Carl's score of 65 was negative 0.43. So he's not as far as negative 1, he's somewhere in here, right, at negative 0.43. That's where his 65 would be. Okay? So now we have a way to calculate any z-score. And notice that if we put the score itself that we're interested in before the mean, we'll find out if it's positive, larger than the mean, or negative, smaller than the mean. Well, there's one more thing we want to be able to do with z-scores. So let's set that up. What we want to do is use z-scores to help us determine which score is relatively better. So in this example, Max has scored a 91 on the biology test, and it had a mean of 76 and a standard deviation of 9. He scored an 89 on the history test that had a mean of 75 and a standard deviation of 8. So relative to the other students in the two classes, on which test did Max do better? Now clearly his score was higher on the biology test. He made a 91 versus an 89, but the tests were of different difficulty. The population of students might have been different. So on which test did he do relatively better than the other students in the class? So that means we want to compare his score to the mean, which represents the other students in the class, and divide by the number of standard deviations. In other words, we want Max's z-score for biology, I'll just abbreviate that, bio, and we want his z-score for history. Okay, and then we'll compare and see on which test was his z-score higher than the mean, right? How more standard deviations away. So on the biology test, remember we put Max's score first minus the mean of 76. How far apart were they? His score and the mean. How far apart? And then how many standard deviations will divide into that distance? So they were 15 points apart, divided by 9 for the standard deviation. So how many standard deviations will divide into that distance? And we get 1.66, and it just repeats. So we would approximate that to 1.67, or whatever our rounding directions were that were given. On the history test, he made an 89. The mean was 75, and the standard deviation was 8. So here he scored 14 points above with a standard deviation of 8. So how many standard deviations divide into that distance between Max's score and the mean? And we get exactly 1.75. So while Max had a higher score on the biology test, at 91 versus 89, relative to the other students in the class, he scored higher or did better on the history test. So we would say that this was the test that Max scored relatively better.